This video is going to show you different ways of representing a double replacement reaction through various different types of equations. Some of it will be familiar, some of it is going to be new. So what we're going to do is everything is going to be based upon the reaction between lead-2 nitrate and potassium phosphate. So to start off, we got to figure out what the products are going to be, right? So if it's lead-2 nitrate and potassium phosphate, hopefully you know that the lead is going to go with the phosphate. So we're going to have lead-2 phosphate as one of the products. And then the potassium and the nitrate will go together. So that will be the other one, potassium nitrate. Okay, so we could very well write a word equation with this. Lead-2 nitrate plus potassium phosphate yields lead-2 phosphate plus potassium nitrate. So these would be our two reactants, or our two products, and they would be on the left side of the arrow, the yield arrow, and then these two would be the reactants. I didn't really do that very well in terms of writing a word equation, did I? All right, so let's get into the actual chemical equations and the different ways you can show that. So the molecular equation is what you're used to seeing. You write the formula for the substance, you put states in it, and then you balance it. So first thing we have to do whenever we write a molecular equation is make sure that we write the formulas correctly. So focus only on lead-2 nitrate. Well, lead-2 lets you know that it's going to be Pb2 plus, which means I'm going to need 2 nitrates to go with it because nitrate is -1. It's going to react with potassium phosphate. Again, potassium is K plus, phosphate is PO4, PO4 3 minus. I don't need that parentheses there. So I need 3 potassiums for every 1 phosphate. And then on the product side, now just because I have 1 lead here doesn't mean I only need 1 lead here. Remember, we're trying to get formulas correct. So I want to write the right formula for lead-2 phosphate first. So Pb's 2 plus, phosphate is 3 minus. So I'm going to have to write the formula Pb3, PO4, 2, in order to make sure that it's electrically neutral, right? Plus 2 times 3 is 6, minus 3 times 2 is 6, so it's electrically neutral. So it doesn't matter at this point that I have 1 lead here and 3 leads here. I have to get each individual formula written correctly first. So same idea with potassium nitrate, K is +1, nitrate's -1. All I have to do is put 1 and 1 together. Again, 2 here, only 1 here. 3 here, only 1 here. Because all I'm doing right now is getting the formula written correctly. Now I can go back and balance. So if I take a look, I'm going to start with this guy. This guy's the most complicated. I got 3 leads here, so I need 3 leads there. I got 2 phosphates here, so I need 2 phosphates there. 6 nitrates and 6 nitrates means I put a 6 out in front, so now I'm balanced. Last thing I want to do is show states. So this is a double replacement reaction. There is going to be aqueous things, and there hopefully is going to be a solid thing. As you look at these two, can you predict which one's going to be the solid? I hope so. All nitrates are soluble for 1, but +2 and -3, that's a strong lattice energy. So this guy's going to be your precipitate. Everything else is going to stay aqueous. So that should feel pretty familiar in terms of a molecular equation. But now we're going to show different equations in terms of just different pieces of information that you get from that equation that you can't necessarily get from the molecular equation. So dissociation equations actually focus on just the reactants. What a dissociation equation is going to do, it's going to show you what happens when we make this thing aqueous. So if we go from PbNO3 to solid, right? When we put it in water, what happens? It dissolves. But it just doesn't become AQ, does it? Since it's soluble and it's ionic, the ions split up. So that's what a dissociation equation is showing you. It's showing you the dissociation of the lead ions from the nitrate ions. Now, I still want to make sure that it's balanced, so I got one lead, but I have two nitrates. And I want to show that they are aqueous, so I'm going to put an AQ there. Some students like to put water as a kind of catalyst because obviously in order to get this to happen, you need to have water available. So that's how I go from my lead nitrate to my aqueous substance. But remember, because it's an ionic substance, it's not really together. It's really separate like this. So dissociation equation allows you to see that it's actually separate. Okay, we got another dissociation equation to write because we have another product. Or the product, reactant. So potassium phosphate, again, if it starts out solid like all ionic compounds do at room temperature, what's going to happen? I'm going to put it in water, mix it up, and my potassiums will separate from my phosphates because they've got a small lattice energy. So I'm going to get potassiums, I'm going to get 3 of them, and I'm going to get 1 phosphate. But again, because they're in ion form, they are aqueous now. They're floating around separate. That's why ionic substances conduct, remember? All right, so those are dissociation equations. We kind of use this idea to help us in the total ionic equation. So what we did here, we're going to emulate in the next one. So I'm hoping that you're following along okay. We're going to move to the next equation, total ionic. Okay, so if you notice, total ionic is going to represent the substances in their true states. That means if you have an ionic aqueous substance, we're going to show it separated. So going back up to the molecular, that's what I'm working off of. I am going to separate the aqueous things in a total ionic equation because that's how they actually appear. Anything ionic and aqueous actually separates like this. The solid is going to stay together because its lattice energy is strong enough to keep everything together. So I want to maintain my numbers. Okay, so 3 lead nitrates means that I'm going to have 3 lead ions, but I'm going to have 6, because 3 times 2, nitrates. So that's how I'm going to write it. I'm going to write 3 lead aqueous plus 6 nitrate aqueous. So that's representing my first reactant the way it actually is in the solution. Likewise, I'm going to do the same thing for potassium nitrate, but notice I have 2 of them. So I'm going to have 6 potassiums and 2 phosphates. And again, they are both aqueous. So there's my reactant side. Takes up a little more room than in the molecular equation because we're splitting the ions apart. So now I got to get to my solid. I'm running out of space here. I have to try and write a little smaller maybe. Now, lead to phosphate is a solid. It's insoluble. So that's not going to change in terms of how I wrote the formula. That's my solid. But my other substance, the potassium nitrate, that's going to be separate. So again, notice I got 6 as a coefficient. So 6 potassiums and 6 nitrates. All right, I squished it all in there. And they are both aqueous. So that is an example of a total ionic equation. Anything aqueous gets split up into its ions. However, the insoluble substance stays together because it's not split up in the solution, so we don't want to show it split up in the equation. All right, so the tricky thing to writing total ionic equations is to make sure that you're paying attention to these coefficients, but also your subscripts, right? You've got to account for all of them. You're almost, if you were to, when you balance this equation, if you were to keep a tally, what would wind up down here as coefficients would be the tally number that you came up with when you balanced. So 6 potassiums on each side, that's what you want to show. 6 nitrates on each side, that's what you want to show. 3 leads, that's what you want to show. 2 phosphates, that's what you want to show. So these coefficients actually maintain the balance. And like I said, if you did an actual physical tally, you would see that these numbers are the numbers that you had when you did the physical tally to balance the equation. All right, so we're almost done. We've got one more equation to take a look at, and that is the net ionic equation. Okay, so there's a couple things in order to get us to the net ionic equation. We're going to use something called spectator ions to kind of simplify the total ionic. So the net ionic is coming from the total ionic. So spectator ions are those ions that don't participate in the reaction. They're spectators, they just watch it happen. So to find a spectator ion, you're going to look for something that doesn't change from the reactant side to the product side. So I'm going back to the total ionic equation. Lead goes from Pp2 plus aqueous to being in a solid. Well, that's changing. So that's not a spectator ion. Nitrate, 6NO3AQ, 6ONO3AQ. That's the same thing on both sides. So nitrate is an example of a spectator ion. Can you find the other spectator ion? There's one more. Hopefully you realize that it is potassium. There's the other spectator ion. So spectator ions are going to be eliminated from the net ionic equation, or from the total ionic equation, and what you are left with will make up our net ionic equation. So one thing I want to point out when we're doing net ionic equations and total ionic equations for double replacement reactions, what really winds up in the net ionic equation are the 2 ions that come together to make the solid. So that's kind of a shortcut way of avoiding looking at spectator ions if you want to. But let's finish this idea. So we've got, for our reactions, we said the spectator ions were potassium and nitrate. There's no need to put numbers in front. We're just identifying what they are. We're not worried about how many there are. But then what's left, our net ionic reaction, is what I had circled before. So it's going to be the 3 lead ions that are aqueous coming together with the 2 phosphate ions that are aqueous to make solid lead phosphate. So I've got the lead ions, 3 of them, and I've got the phosphate ions, again 2 of them, to make our electrically neutral, sorry, I had a brain pause there for a moment, electrically neutral solid. So there you've got the net ionic equation. It's showing what's important. And what was important, how do we know a reaction took place? Because that precipitate formed. So the only 2 important ions are the ions that go into making the precipitate. The other ions are doing nothing. All right, so that is your first example of doing the different types of reactions. What I'd like you to do now is pause the video and try doing this equation. And we'll come back in video number 2 and take a look at what you did. Hopefully you were successful at doing everything. So try doing this practice one before you actually look at the answers in the second part of the video.